Okay, let's dive right into this explainer. Today, we're going to completely shatter a foundational myth of computer science, the idea that cryptographic hash functions actually destroy data. For decades, we've treated these complex algorithms like digital black holes, right? Places where information goes in and gets permanently erased. But what if I told you that the data isn't gone at all? It's just hiding.
To make sense of all of this, we're going to follow a pretty clear roadmap. We'll start with the illusion of erasure, compare floating versus pin seams, look at how data actually lives in the change, measure the hidden residue, explore the empty hash carrier, and wrap up by totally reframing cryptographic inversion.
All right, part 1, the illusion of erasure.
Does cryptography actually destroy data? Well, if you look at most computer science curriculums, they'll tell you that hashing a file, say with a standard like SHA-256, washes the original data away through irreversible thermodynamics. Basically, they're saying it gets tossed into a digital blender and just ground into a smoothie of zeros and ones. But we're challenging that absolute rule today because the math, it shows us something completely different, and honestly, something way more elegant.
Think about this through the lens of what we call fold tomography. If you use a simple origami metaphor, it becomes really clear. Those bits aren't being ground into dust at all. They're actually just being folded up into a really tight topological knot. And here is the secret. The history of that paper, every single fold, every little crease, remains completely intact right there inside the knot. We just need the right geometric lens to read it.
Moving on to part 2, floating versus pinned seams.
So the Bailey-Borwin-Plouffe, or BBP formula for pi, is essentially our Rosetta Stone here. It's this brilliant spigot algorithm that lets you extract any digit of pi directly, and it does this by using a floating seam. That just means the computational transition point moves perfectly with whatever digit you're trying to find. It's basically a printer for pi. Now, on the flip side, SHA-256 intentionally engineers that printer right out. It uses a pinned seam that's locked at a very specific point, creating a universal choke point that forces all the data through the exact same gateway.
Let's break down exactly how that pin seam works in SHA-256. For the first 15 words, the algorithm just takes in the raw message, totally fine. But exactly at words 16 and 17, the geometry fundamentally shatters. The algorithm violently shifts into complex fractional extraction. And because the seam is pinned at the exact same spot for every single message, exponentially vast permutations of different inputs are forced right through it. So the really crucial takeaway here is this. SHA-256's one-wayness is actually just address-occlusion. You aren't destroying the data, it's more like you just lost the claim ticket to the code check because everyone was forced to walk through the exact same door.
Which brings us to part 3. Data lives in the change.
I want you to consider this profound shift in how we think about this. Value is not a state. Value is a sequence of folds. In traditional thinking, we usually look at the final 256-bit hash digest as the fundamental value of the message. But the physical reality of this computation, that final digest, is really just the last page number of a very long book. The actual value resides entirely in the iteration, the highly specific sequence of pages that were flipped to get to that final coordinate.
This tells us we need to look at the change, not the value. You see, the SHA-256 round function is actually completely bijective. That means it is a perfect two-way street. Literally nothing is destroyed inside the rounds themselves. And because of this, the original message word can be perfectly recovered purely from the round-to-round deltas. If you have two adjacent states, the message word that bridged them together falls right out by pure algebra. The message lives cleanly inside the changing state, not in that final scrambled output.
Okay, part 4, measuring the hidden residue.
By analyzing the cryptographic wash, researchers found a really distinct 3-round parity envelope. They measured exactly 2.66 bits of excess mutual information between adjacent rounds. So what does this actually mean? Well, it means the structure that the hash is trying so hard to hide is actually screaming through the data, but it only lasts for a horizon of exactly 3 rounds. And this corresponds perfectly to how deep the SHA-256 algorithm actually scrambles data on a local level.
But right after that parity envelope decays over those 3 rounds, something else really interesting happens at round 4. A sharp, distinct carry echo perfectly fires at lag 4, exceeding the baseline noise by 0.12 bits with a massive amount of statistical certainty. It's a completely isolated echo, entirely distinct from that 3-round parity decay we just talked about. Now, what is super fascinating is figuring out where this lagged 4 echo actually comes from. Is it caused by the complex message schedule, or is it the physical register pipeline? Well, the data definitively proves it's the pipeline. Check this out. The lag4 echo is actually slightly stronger in the first 15 rounds, where the complex recurrent schedule isn't even active yet. This absolutely proves that the data's residue is tied directly to the physical 8-slot register pipeline latency of the algorithm itself.
Moving right along to part 5, the empty hash carrier.
Think of the empty hash, that's the digest you get when you input absolutely nothing, as a standing wave on a vast ocean. When you input a message, you aren't suddenly injecting new entropy or bloating the size of the wave. Not at all. Your message is really just a ripple that changes the wave's phase.
When we map out these phase delta signatures, we see that whether the message is a single letter A or the word hello, the total Hamming weight envelope, which is basically the total density of the bits, remains strictly balanced right between 108 and 147 bits. The overall amplitude of the system literally never changes. The message only alters the specific rounds that deviate from the baseline. It just alters the phase coordinates of the carrier wave, shifting its position around in an 8-dimensional space.
And finally, part 6, reframing cryptographic inversion.
If we frame the physical mechanism of hashing not as this chaotic, random scramble, but as a rigid sequence to fold, compose, and read, we completely change the game. We are entirely reframing cryptographic inversion here. It's no longer this impossible thermodynamic search through an infinite universe of possibilities. Instead, it becomes an elegant, highly structured process of phase demodulation.
What this means is we can actually triangulate the true message. You start with the known public identity, the empty hash carrier. Then, you map the public geometry of the round function and measure the specific phase deviation of your target hash. By subtracting the carrier phase, you can treat the empty hash as a gravitational carrier, reading the perturbation directly. It is exactly like pulling a hidden signal right out of a radio wave. You're reading the shape of the distortion to find the exact data that carved it.
So, as we wrap up this explainer, I want you to consider the massive implications of what we've just covered. If cryptography merely folds data into accessible geometric shapes, what does this mean for the passwords, blockchains, and encrypted networks we trust with our lives every single day? And honestly, what other supposedly irreversible systems out there in computer science or even in biology and physics are just waiting to be phase demodulated? The absolute limits of computation might just be much deeper and way more reversible than we ever imagined.